We deploy artificial intelligence in the workplace to optimize for velocity. The logic is simple. If a tool can automate the execution of a task, it frees the human to produce more volume in less time. But executing a task with an automated tool is an entirely different cognitive process than acquiring the underlying skill required to perform that task independently. When we offload the friction of problem-solving to a machine, we risk bypassing the exact mental processes necessary to build human expertise. Relieving cognitive load with technology is a familiar practice. The introduction of electronic calculators in classrooms removed the burden of manual arithmetic, allowing students to focus on higher-level mathematical logic rather than basic calculation. Later hardware deployments, such as providing students with standard internet-connected laptops, yielded mixed educational results. The technology provided access to information, but access alone did not guarantee that students would absorb or synthesize the material effectively. Large language models, or LLMs, AI systems trained on massive datasets to generate complex, human-like text, present a completely distinct set of risks. Unlike a calculator, which is deterministic and entirely reliable, an LLM handles highly complex intellectual reasoning, but remains highly fallible. This creates a compounding structural problem. Because LLMs suffer from hallucinations, generating confident but factually incorrect responses, users must vigilantly verify their output. If users rely on the AI to do the heavy lifting from day one, they never develop the baseline domain expertise required to catch those inevitable failures. To measure exactly how generative AI impacts skill acquisition, researchers from the University of Pennsylvania conducted a massive field experiment. Published in 2025, the study tracked nearly 1,000 high school mathematics students in Turkey across multiple review sessions. The researchers designed a randomized controlled trial, dividing students into 3 distinct treatment arms. The control arm studied using traditional textbooks. The GPT base arm received unrestricted access to a standard ChatGPT interface. The GPT tutor arm used GPT-4 with hidden guardrails designed by teachers. By structuring the trial this way, the researchers could isolate the exact cognitive effects of standard AI interfaces. They could measure precisely how the human brain retains new information when assisted by raw generative AI, compared to traditional study and safeguarded AI. The experiment proceeded in 2 phases. Phase 1 was an assisted practice period. Students were given a set of complex math problems and allowed to use their group's assigned resources to solve them. This chart tracks the normalized student performance during that practice session. The control group, relying strictly on textbooks and their own notes, achieved a baseline normalized score of 0.28 out of 1. The students in the GPT base arm saw an immediate, drastic spike in productivity. With unrestricted access to standard generative AI, their performance improved by 48% over the control baseline. The GPT tutor arm performed even better. Guided by the safeguarded AI, these students logged a massive 127% improvement over the control group. These Phase 1 results mirror the exact narrative driving enterprise AI adoption today. Give a worker a standard AI tool, and their immediate output drastically increases, largely by elevating the performance of the lowest skilled individuals. If the analysis stopped at this exact moment, the data would heavily imply that AI unequivocally revolutionizes both cognitive output and human mastery of complex subjects. But the experiment had a second phase. Immediately following the practice session, the researchers physically removed all laptops and AI access. The students were then given a closed-book, unassisted exam. Every problem on this unassisted exam was conceptually identical to a practice problem the students had just solved. If they had actually internalized the logic during Phase 1, that knowledge should directly translate to success in Phase 2. Looking at this updated chart tracking unassisted exam performance, the data completely inverts. The GPT base group's performance collapsed to 17% below the textbook-only baseline. Having unfettered access to a standard GPT interface actively damaged their capability. Spending an hour working alongside raw AI resulted in less actual skill acquisition than simply reading a book. Meanwhile, the performance of the GPT tutor arm leveled out entirely. Their scores dropped from their massive practice peak to become statistically indistinguishable from the baseline control group. Post-session surveys revealed a severe perceptual blind spot.
Students in the GPT base arm reported no awareness of their cognitive deficit. Despite failing the exam, they subjectively believed they had learned just as much as their peers. This is the productivity illusion. Standard generative AI creates an artificial sense of mastery by outputting high-quality work on our behalf, a mirage that completely evaporates the moment the user is forced to operate independently.
To prevent this specific degradation in the workplace, we have to understand the mechanism. Why did standard GPT access actively damage the student's ability to learn? The researchers first tested the model hallucination hypothesis. GPT-4 regularly makes errors in mathematical logic. It was entirely possible that the AI was feeding students incorrect steps, actively teaching them the wrong methodology. The error rate supported this suspicion. When prompted simply for an answer, GPT-base provided the correct math only 51% of the time. The vast majority of those failures, 42% of the total output, were deep logical errors rather than simple arithmetic mistakes. To test if these errors caused the exam failures, the researchers utilized a problem-level regression analysis. A regression analysis is a statistical process used to determine if one specific variable directly influences another. They checked to see if an AI logical error on a specific practice problem correlated with a student failing that exact counterpart on the exam. The regression showed absolutely no statistical spillover. High logical error rates from the AI during practice did not correlate with higher failure rates for those specific concepts on the unassisted exam. The students weren't failing because they had absorbed bad logic from a hallucinating AI. The data indicated they were failing because of their own behavioral interactions with the interface. The students used the AI to bypass the friction of learning entirely, treating the model as a cognitive crutch. To verify this, researchers used natural language processing, or NLP, a computational technique to systematically analyze and categorize large volumes of text data. They processed the actual chat transcripts between the students and the generative models. They categorized the student inputs into two camps. Superficial prompts consisted of simply copy-pasting the question or directly asking, "What is the answer?" Non-superficial prompts were substantive interactions, like attempting an answer first or asking for a step-by-step hint. This chart tracks non-superficial conversations. For students in the GPT base arm, the line flatlines near the bottom, representing purely superficial demands for answers. But look at the contrasting GPT tutor arm. Their willingness to interact deeply climbed steadily upward over the 4 sessions. Without guardrails, human nature defaults to the path of least resistance, allowing GPT-base to act as an automated answer key that short-circuited the skill acquisition process. If standard AI acts as an intellectual bypass, how did the researchers engineer GPT Tutor to neutralize the 17% learning deficit while still keeping students highly engaged during practice? The difference lies entirely in the system prompt. While GPT-base used a naive, single-sentence instruction to act as a helpful assistant, GPT Tutor ran on a highly structured architecture containing strict hidden variables and constraints. The first vital guardrail addressed the hallucination problem directly. The system prompt physically contained the verified, correct solution to every practice problem, completely eliminating the model's need to guess the mathematical logic. The second, and most crucial, guardrail targeted the behavioral problem. The LLM was strictly instructed to never reveal the final answer to the user under any circumstances. Instead, it was restricted to providing step-by-step hints. To enforce this, GPT Tutor was preloaded with a matrix of common student mistakes, alongside specific pedagogical responses mapped directly to each anticipated arrow type. This design explicitly forces desirable difficulty, the psychological principle that genuine learning actually requires cognitive friction. GPT Tutor worked to halt the skill degradation precisely because its system prompt artificially re-injects friction back into a tool originally designed to erase it. Generative AI, by its default design, optimizes for task execution. It does not optimize for human capability. The guardrails placed on GPT Tutor successfully stopped the bleeding, preventing the severe 17% drop seen in the standard interface. Yet, importantly, even with those strict safeguards, the AI still failed to elevate unassisted exam scores above the baseline textbook control group. To actually elevate human learning, future AI systems must evolve from passive chatbots into proactive pedagogical agents,
AI systems designed to actively probe users, identify misunderstandings, and guide them, rather than simply waiting to fulfill a text request. For developers, educational technologists, and corporate engineers, the data is clear. Deploying unfettered ChatGPT-style interfaces for training and education purposes is actively counterproductive. Prioritizing immediate workflow velocity over long-term skill acquisition will hollow out the specific foundational expertise required to verify and maintain high-level knowledge work. Designing effective systems requires engineering models capable of withholding the answer until the human user has earned it.